Hello and welcome to lecture 16. So today we're kind of shifting gears. So we spent the first 5 weeks of this course covering hardware design, Scala, Chisel, and a nice cycle and kind of getting better at all three of them. And now to kind of get ready for the project, we're kind of shifting gears, thinking more about hardware design more generally. So less about exact details of Scala and more about just what happens when you're trying to design hardware. What does it mean to think about physical constraints in hardware? So we see that in a few lectures this week, right? So today is going to be talking about design optimization, as well as memory, which is a really important thing. It's the first thing you should be optimizing in your design. And then we'll be moving on to additional topics this week. And so this material perhaps overlaps some things you've seen before, but I guess what makes it interesting, number one, including it, make sure this class is inclusive. We aren't expecting everyone to necessarily be a EE major in this class, right? But number two, the high level perspective of some of these physical things you may understand deeply may also be insightful, right? To kind of see how do we think about these deep physical problems from a high level point of view, from a architectural point of view, from a agile design point of view. Okay, so like I said, talking about physical design today, that is how do we go from a idea for a chip to an actual chip. There's some steps in between we haven't been covering at all this quarter. Talk about memories and how to actually make memories much more efficient. Okay, so naturally the question is why should we do this? Well, if you optimize your physical design, the number one thing you're probably going to improve is efficiency. And efficiency relative to what? Well, that depends. But the real question, of course, is when is the effort worth it? And it's not an issue of is your design efficient or not efficient. It's not a binary quantity. It's more just how much time and effort can your team put into this project? How much time or effort should you put into this project, right? And as you put additional effort in there, um, you hope they're getting gains, not wasted. But is that additional gain worth it, right? Um, and so think about usage case, right? Usually have some sort of performance target or something or some sort of cost target. And the question is, how are you going to get there? Now, if you have just absolutely bare minimum performance objectives, perhaps their answer is just to not design custom hardware, which is make it sad, but that might be the right answer. The right answer is simply just buy a microcontroller, put software on there, and boom, you're done, right? So building hardware as a custom design there's some motivation, right? Some reason why you're doing this. And usually there's some efficiency or cost reason for doing that. Because otherwise you would just put software on a microcontroller, right? And so the reason why I bring this up is that means you do need someone concerned about physical design, right? You can't just completely ignore it. Can't just forget about that for later on. You should have some reason why you're doing that. And so we're preaching this class is thinking about optimized physical design in various places in various ways and being very mindful of what benefit you're getting and what you're paying to get that benefit. Okay, so what can we actually optimize for? Well, it turns out when it comes to hardware, there's three metrics. So in software, it's just performance, how long does a program take? In hardware, there's three. There's power, performance, and area. You may have seen PPA as an abbreviation used in this class and elsewhere, but all these things have real important consequences, right? So for example, power, as we're all familiar, uh, for mobile devices, we're very conscious of, of course, power impacts battery life. Make our design take less power. We can have a longer battery life or a smaller battery. But there's other ways power comes up, right? If you can reduce your peak power consumption, you can reduce, of course, the peak heat it produces in thermals, right? And as a result, enables a lot of things. At the large scale in data center, many of those chips are completely power limited, right? Those big GPUs are, pulling hundreds and maybe even close to a kilowatt. Um, that's a problem, right? If they get that power efficiency improved, they would use it to do more, right? And so for many people, power is the limiting factor. Additionally, even in a mobile design, not just battery life, but peak power matters, right? You don't want someone to burn their hand holding your handset, right? It's no problem. And then, of course, things like, power over time is energy, which, of course, what you pay for when you pay for electricity bill. Yeah, that matters, right? If you're paying for a big data center, you want to, of course, reduce that bill if you can. So power has a lot of consequences. There's also a cost of the physical device to what kind of power delivery system you need in your product. If you take apart an iPhone or some other device, you'd be surprised to see how many devices, both in terms of volume and cost, are involved with power supply and delivery, right? So if you can reduce your power consumption, you can make those devices smaller and cheaper. Power really matters. Why it's first. Um, Performance, of course. Like I said, we're doing this because you have some sort of goal, right? If you had no performance goals, we wouldn't bother making a custom chip. We would just write some code, use a CPU, and be done with it, right? So you have to have some sort of performance goal. And of course, performance is measured by how fast you complete your application, not necessarily by how fast your clock period is, right? And so You can have many or greater or fewer number of cycles, but really matters how fast your application is accomplished. And then finally, is area. That is, in other words, how big is your hardware design in terms of hardware resources. On an ASIC, of course, that's actual millimeters squared. That's, has a direct cost measurement. Versus FPGA is how big of a FPGA do you need, how many FPGA resources do you need, but area is basically a proxy for cost. Cool. It's very broader now, but I haven't taken any questions along the way. Okay, let's keep going. So let's say you decided, not decided, you should go about this optimizing your design for physical design. And so what are you gonna do? Well, you need to have a goal. You can't just say make it good, right? What does that mean? It's unspecified, right? So first, you need to have what implementation technology you're working with, right? So perhaps you're using a specific ASIC technology process. I'm going to use TSMC 10 nanometer or something, right? Or perhaps you're targeting a certain FPGA. You need to know how you're implementing this, right? And so this is really important because this kind of sets the rest of the story. So in software, it's like you can write code and you can write it on one platform. And for most of the code you write in a high level language, it usually ports about issue to another processor, right? And so you can do most of your time and not even knowing what the final processor is going to be like, and it kind of works out, right? Not the case for hardware, right? When you pick a technology, it's the first thing you need to do. That really can kind of set the bounds for everything else you're thinking about, right? Additionally, when you start trying to optimize it, you need to pick which metrics matter in terms of things like PPA, power performance area, right? The tools can't just say, make it good, right? You need to say, okay, I want you to give me, of those three variables, you got to start constraining them. So, okay, well, given this area limit, I want you to get me the best performance you can. Maybe we'll sacrifice power, right? Or something. So you got to kind of pick what you're kind of constraining versus optimizing, right? So oftentimes you tell tools to go after clock rate or area, but there's a third dimension there to tell how to kind of give it up on that. And so as I kind of pitched in this course was agile philosophy, rather than just trying to do everything in the beginning, get a process going, close that loop, see the big picture, get some numbers out, right? See, okay, well, here's my initial design. I know my design is not done, but I might as well start seeing where the area is going, where the time is going, where the power is going, so you can see how you're doing, right? And perhaps you have certain targets and you've already reached those targets. Guess what? You can stop early, right? No reason to keep grinding for no reason. Um, and so then you can kind of start assessing, okay, wait, we're not at our target yet, or we know we got to add a lot more functionality, and functionality is taking a lot of area. How are we going to make room for it? Start thinking about, okay, well, what's going to give us the most bang for a buck? What's the most beneficial, etc. Um, so definitely measure first is kind of, so I one thing bold this entire slide. And so for this course, we talk a lot about hardware generators. Why is this so exciting? Well, a hardware generator makes it easy to turn those knobs, right? If you have a generator rather than a rigid design, you can go in and change it to match this thing. I actually came across just the other day this repo that's getting shared on LinkedIn. And someone said, "Oh, here's my system Verilog repo. Implements all these great data structures in system Verilog. Look, I got tests. Isn't this wonderful?" And you go and start scrolling through it, and you see some, using things in the README like, "Well, these are what I think is the right set of parameters. But if you need to change it, feel free to change the code." Right? It's like, yeah, this is not parameterized, right? Like it's very much rigid and locked in. There are some parameters in system Verilog, but not the same way we can do with generators, right? And so this is why we want generators. We want to be able to kind of turn the knobs when we need to, especially for things like optimizing physical design. That's when you really want those knobs to exist. And fundamentally, it's simply you need to make some trade-offs between those things, right? Oftentimes, you're going to improve one at the expense of the other. If you can improve one metric at no cost to the other metrics, that's great. Do it. One second. If you're in that situation, that's a no-brainer, right? Obviously, if you can make power better at no consequence, no loss of performance, no loss of area, you should do that, right? Usually, when you're doing competitive design, you're at a point where to improve something it costs something, and then you got to weigh those trade-offs. We'll come back to this later this week in what we call design space exploration, but that's what we'll bring back to. I saw a question. Was there extreme parameters in Chisel versus parameters in Verilog? Good question. So in Verilog, or I should say System Verilog, you can have numeric parameters, right? So that's totally doable. And for some things, and some really clever System Verilog implementers, you can use that. But for some of the things that we do in our chisel and our generator, it's not so much just the parameters, it's how you use those parameters, right? You've seen examples already of us doing like recursive things to build topologies internally based on those parameters, right? Versus in Verilog, you're kind of constrained to things like a genvar. And for those of you who are Verilog experts, I know this may aggravate you, but I'm also constrained this to things that are synthesizable. There's plenty of things you can do in system Verilog simulation we're not even talking about right now. But more generally, It's not so much the parameters; it's the programming language that glues it together in Scala, that lets you do all sorts of cool things. Additionally, you can have things that are not just numeric parameters, as parameters in Chisel, right? You can have a parameter be literally a function. You can have a parameter be an object, right? You can do things totally typed if you need to. Cool. Other questions? Great. Okay. Um, so, uh, continuing on this thread of differences between what's going on in software versus hardware design, um, people may be very used to the software. That's kind of what I designed this course for. I'm going to call it the easy world. And I put the quotes on that because, of course, it's not easy, but it's comparatively easier, right? And the reason why when you're writing code, you spend all this effort writing the code, getting it correct, you verify it, but then you're basically done, right? You might spend some time thinking about performance, right? Make sure you don't have any quadratic algorithms. We should have linear algorithms and that sort of stuff. Um, but for the most part, things are very portable. If you make your code faster on one CPU, it's probably gonna be faster on another CPU. And you have your giant code base and you pan it off to your compiler tool flow, and it just churns through it. And not only is it going to produce correct code, it's going to do pretty good optimizing. You tell it, okay, give me O2, right? And it does a pretty good optimization level. You don't say, give me O2, but trade off this for that. That's not usually what you do. You can say minimize for size, for example, but usually O2 does that pretty well on its own. Um, the key thing is it doesn't really break, right? If you're writing software and your compiler produces incorrect code, you should rightly be angry. I've been programming for, I guess, a good number of years now. I've encountered it only a few times, and the few times I've encountered it, it's all been the same compiler. That compiler is dead to me. That's ICC. Dead to me. I will not use that thing again. Because it's hard to get your code right the first time. If the compiler is emitting incorrect code, it's that painful. But the answer is most of you in your career probably have not already or probably will not encounter an incorrect compiler, right? Like they're pretty good at crashing themselves before they produce bad code. Um, that is absolutely not the case in hardware design, right? So now in the air quotes hard world, hardware design, right? Getting it functionally correct is just the beginning, right? Actually getting a working chip is a whole other level of complexity and effort, right? In terms of optimizing the physical design, verifying it, making it manufacturable. These are all large hurdles requiring a lot of effort, a lot of people, a lot of stuff, right? And in addition to just saying optimize it only for performance, now we have this PPA. We have three metrics to optimize for. And if you're optimizing for these are very implementation technology specific. Remember earlier I said you want to pick an implementation technology early on in the project, saying I'm going for this ASIC or this FPGA technology. The reason why is realizations are going to be different, right? How you optimize for an FPGA is different than how you optimize for an ASIC. And so you kind of need to know what you're targeting right away. And it's big detail at the end. The tool flows are much worse, right? You both need more human effort to get them to run. And they also need oversight, right? They do frequently make mistakes, right? You may have heard of things called like LVS or DRC. These are additional passes we run because we know the tools are going to make mistakes, not just some of the time. On a larger design, it's going to make a mistake every time you run, right? So you need things like DRC and LVS to make sure you can find those mistakes. So yeah, it's rough. So fortunately, in this course, we aren't actually going to run the physical design tools, but I want people to be aware of these concerns. In this course, we are going to talk about optimizing those. So what would it look like in terms of the Agile point of view of how would you change your design to optimize it once you get that feedback from these tools? Cool. Question, yes. Why is ICC dead to me? So from a minute ago, I complained about a compiler. Yes, as I said, it produces incorrect assembly. No. So I happened to me twice in my career where I did plus code that we managed to get down to like an 8-line minimum viable thing. There's nothing weird that could cause it to uh, produce flat out incorrect assembly. And so the first time I was at Diligent Graph student, I reported it, and they did nothing with it. And many years later, that same code will still cause it to break. And then years later, after I finished my PhD, I got a bug report from my code base, and I went in and found out that nope, it really was ICC again. And I once again pruned this big code base down to a minimum viable example, about 25 lines, and it still caused it to break. And so yeah, it's buggy. It shouldn't be buggy, but it is, and so that's why I this is weeks of my time I lost because someone didn't want to make the compiler more robust. Cool. Other questions? Okay. So we saw this in the very first lecture, right? We talked about two different hardware design philosophies, and these are extremes. These aren't, exactly what you would follow, but in the waterfall style, you do every step complete before moving on to the next step. So you have this complete end-to-end design in full detail. You think a lot about that. You do a lot of design reviews, then you specify things in more detail. You actually implement each piece in isolation. You integrate them, you optimize and verify it. And the problem with this is that until you get to these later stages, like optimization, integration, and verification, you actually don't know what your total cost is going to be. You know what you budgeted your total cost to be. You know, okay, I think this is going to take this much area, this much power, this much performance, but you don't know for sure. You can budget it out. Okay, so let's say I have, a certain amount of area. Okay, I'll give this much area to this block, this much area to this block, and you tell each block, okay, you got to fill in that area. If all your blocks fit in that area, great. But maybe some team comes back to you and says, you know what, we can't quite fit in that area. We need more area, right? And so it's kind of this moving target. We have this plan, and the plan, if it's correct, then sure, it works great. But some things are really hard to get right in advance. If you're doing a very incremental change, you have a chip that already works, you'll make a small 5% change, sure, you know these things cost. But if you're writing something completely from scratch that's never been built before, how can you estimate some of these things? It's actually really hard to do. And this is kind of why I want the agile approach, where you know what? We're going to keep having numbers and able to keep optimizing and verifying these numbers, right? So in other words, you know the cost right away because you actually push it through the tools right away. And so you keep going through the flow. I'm going to make my hand match the circle. But yeah, cool. So for those unfamiliar, what are the main stages in the chip design flow? Well, typically you start with RTL. So in that case, with something like Verilog. And at the other end, you have the working chip design. So in software, you're just running a compiler and boom, you have a program, you're done. In hardware, is actually a number of different tools, a number of different phases, which I've grossly oversimplified as three phases. Synthesis, turning your RTL into actual technology devices, placing them onto the system, and then of course routing the wires between them. That is grossly oversimplified. But I'm still showing to kind of remind folks there's these different stages, and you can have issues in various stages. And in the real world, these tools usually aren't just a single linear flow. There's often, you know, phases that repeat themselves, they have feedback, whatever. And so even just maintaining this tool flow is actually usually quite a task in itself. Um, Very common thing, let's say you have a very smart tool flow that, is trying to optimize a certain performance target in terms of clock period, and you identify as it's not making that clock period. It goes and finds that critical path, when it's too long in terms of time, and tries to do what it can to shorten it, right? So maybe it can better place and better route the wires for that. If need be, it can even resynthesize some of the gates in that critical path, make the logic stuff shallower, or use higher power components that are faster to do whatever it can, right? And so you can see by doing that, even that tool flow itself is taking a more agile process. Rather than doing waterfall of synthesis, placement, routing, et cetera, it's actually now doing it through all the way to the end, seeing what's wrong, going back and trying to fix it, right? And so yeah, even the tool flows are kind of going more agile like, even though they don't even realize it. Um, and of course, there's a lot of steps usually unfortunately involve a lot of humans trying to fix things along the way when things don't go quite right. And one thing I didn't even talk about, of course, is verification, making sure it's correct. Yeah, building a chip is tricky. Okay, so given that context, let's talk about memory. So why am I talking about memory? It's often one of the most significant costs in hardware design. Other than Bitcoin mining, virtually every workload people care about requires a certain amount of data, and that data is usually too big to fit entirely on chip, right? And so because of that, we have to have memory, both on-chip memory and off-chip memory, and that really impacts cost, right? And that really sets the entire stage, right? So off-chip memory, of course, that adds a lot of cost in terms of components and the integration. So you may be familiar with, for example, DDR as we use often in our laptops and servers. But then for things like GPUs, of course, there's GDDR and even HBM. HBM, of course, is the highest performance, but it's also the most expensive to integrate, right? So that's a lot of cost. If you could get by with using GDDR instead of HBM, that's going to save your team a lot of money, right? Um, on chip, a lot of designs are at least half of their areas spent on chip memory, SRAM. Look at like a CPU die. Definitely half of your on-chip area is going to be spent on cache, right? Even on a GPU for doing AI, a large fraction of that area, if you actually look at what it is a sum effect memory, whether it be actual caches, whether it be the scratch pads, whether it be the register files. And so, yeah, memory is extremely important. It's one of the most important cost things. And so, what can we do about that? Well, it could be worth a few things, right? It also can limit performance, right? If you have offshore memory, of course, latency is a big problem. But also bandwidth is a big problem, right? Like I said, that's why people are using HBM because they want that bandwidth. The other memory technologies aren't sufficient, right? And so, yeah. And so, of course, why are we in this conundrum? Well, you need memory to hold the data, the application data, its intermediate state, everything else. And here's one interesting way to think about memory, which I think is widely appreciated. Think about memory as a connector. So in this course, we've been thinking a lot about hard designs, You see me draw schematics that kind of look like graphs. There's this gate attached to this gate, or this component attached to this component. You write your chisel. I'm instantiating these components and connect them together. So that connectivity is very static. Memory allows for much more dynamic connections, right? You can have write something to a memory location in one cycle, something else later on can go read that data. So in a way, it's like that thing that produced it and the thing that consumed it communicated, but rather than having a direct wired connection, they instead wrote to memory and read it back from memory, right? And so sometimes people refer to memory as a way to communicate data in time, right? You put things in there and if things come back there, and it's this kind of all-purpose connector, right? In a sense that, with your normal hardware data path, you have this producer is wired to this consumer, very clear wired connection versus memory. You chuck things into memory and then, you pull them out later on, right? And so as a result, you don't know the producer-consumer relationship in advance. That's an interesting detail that comes as an architect trying to optimize all this, but the result, of course, is the memory is there. We need it, and it has all these challenges and costs. Cool. Okay, so to get everybody on the same page, let's talk about terminology for memory. So, of course, first off, there's a capacity, how many bits or bytes it holds. These days, I think bytes is the most common unit, but of course, people often may use bits, and we also use words. And of course, words, you got to worry about how big the word is, a 32-bit, 64-bit word, etc. Latency is the time to retrieve data or complete a write, sure. Bandwidth, in this case, talking about the data rate, right, in terms of bytes per second. Talk to enough people in electrical engineering and hear bandwidth, they always think of, like spectrum. It's like, that's not quite what we're talking about here. We're talking about actual data rates. And so you have to interact with memory, what we call a request, right? So we can say, hey, memory, give me a read. I want to read this location. Or hey, memory, write this data. And so that's a request. These requests come in on a port, right? So you can have a read port or a write port. So read port, of course, you need to say, hey, this is the address I want to read. You set 1 to mark, hey, I'm performing a read. I'm enabling this action. And then you get the data back out some latency amount of time later. And how much data that comes out is the access width, sure. For the write port, of course, you also need to say, hey, I'm doing a write. You give it the address and the data, right? The data goes in. Now, it's the read port, it's the write port. You can also have a read/write port, sure. Um, and this is an important constraint because it actually comes down to circuit level building memory. Sometimes the memory technologies have a limit to how many ports they can have, right? So, for example, like in DRAM, you typically have one read/write port for an entire, at least NAT, this is terminology inside of DRAM, deep inside there. At the higher levels, you can definitely make it seem like there's a lot more, but at a MAT level, you basically have only one read/write port. And SRAMs in the CPU, you can have one read/write, maybe two read/write ports. You can go higher than two, but usually it's pretty expensive. Um, and so there's various constraints. On FPGAs, using BRAMs, you get two read/writes, etc. And then, of course, there's other term, requests in flight, which is if you have a significant amount of latency, you may want to have multiple requests in progress at the same time. So there's, I have request A, request B. And yeah, so the memory has to kind of be able to differentiate those two requests. Cool. Questions? Okay, so kind of rounding out these fundamentals. If you take an architecture class from me, you see me rant about Little's Law, and you're not skipping it out in this Agile hard design class. I love Little's Law. It's a simple, simple equation that explains so freaking much about architecture. So what is it? Well, it's the relationship between throughput, latency, and parallelism. In particular, how they're all working together. So people may say, oh, well, isn't latency just 1 over throughput? And the answer is sometimes, right? And why is it sometimes? Well, if the parallelism is 1, sure. But now if I have two things in flight at a time, then of course the throughput is twice 1 over latency, right? Because I'm doing two things at a time, right? And so this is all based on averages, but this helps you understand certain trade-offs, right? So very commonly, as an architect, for example, working on memory, latency is hard to reduce, right? We want to make the circuits faster, like we make it so much faster. So latency is fixed, but I'm not getting the bandwidth I need, right? So in order to get this throughput I need to increase parallelism. It's a very common consequence, right? Or maybe, let's say, for example, you figure out a way to reduce latency and your parallelism is fixed. Well, then that means your throughput jumps, right? For example, or you can use turn knobs various ways. So you can always turn these knobs different ways. We can see this is the relationship between them. Cool. Okay, so let's start trying to build up a methodology for optimizing memory. So like I said, typically the goal is to reduce costs in a way that is not hurting performance or perhaps even reducing performance detriment of memory. Okay, so where are the pain points? Normally, memory latency is too high is the biggest one, right? If you have offset memory, we're talking, 50, 100 nanoseconds, and your clock frequency on a speed design maybe in a gigahertz range. So in other words, talking hundreds of cycles to get the memory. That can be a problem. Another common challenge in memory is you don't have as many ports as you want. You have, let's say, 100 units that want to talk to this memory, and you only have, two ports in that memory. How do you handle that, right? Another very common consequence is how do I get the bandwidth I need, right? I need more bandwidth. I want to get more bytes per second. How do I get there? And so this is really an architectural kind of problem. So what can you do? Well, number one, be very clever about using the memory, right? If you can get by with fewer bytes, do that, right? Because then you can use a less memory, less components. That's cheaper. Also, you want to use the cheapest memory you can, right? So even though HBM is the fastest memory we often have, it's super expensive, right? So we would love to avoid using that if we can. And so if you can get by with lower memory technology, that's better, right? Architecturally, you want to make a design that can handle high latency, right? So if you have ability to tolerate high memory latency, that's great. Things like caches and CPUs help for that, right? And then finally, being clever with how you use your data, right? If you can reduce the bandwidth you need, once again, you can use cheaper memory or less memory, reducing your costs. So these are things you kind of want to do. Um, as I said before, there's a number of different memory technologies. You're kind of constantly looking at the trade-offs. And in general, it kind of follows hierarchy of the ones that are most expensive is because they're the least dense. You get the fewest bits per square millimeter and unit cost. And they often require a lot of energy, but then at the other spectrum, you get really cheap bits, right? So from the fastest to slowest, yeah, registers, of course, very fast. SRAM, DRAM, phase change memory, which I guess is on its way out, flash, hard disk, you can keep going, right? But from the Agile hard designer point of view, you're talking usually about SRAM registers, offshore memory, and offshore memory can usually be, HBM or DDR or something. Cool. So let's see some tricks we can pull to make memory work out better for us. First up is something called banking. So basically, when you're trying to build something, you'll see you've chosen implementation technology. I'm going to build with this foundry process in 10 nanometer. They'll often provide you with the SRAMs for that process. Okay, so I have their SRAMs, which are blessed by this foundry. They have the following properties. You check the specs on them, and you realize, oh wait, that's not enough bandwidth for what I need to do. Um, so maybe in this trivial example, let's say I want to use the memory from the foundry that has only one port, but I have two consumers. And so how can I deliver two ports worth of bandwidth to handle this, right? Um, so normally at first you might say, oh, well, if I need to get double the bandwidth, maybe if I can reduce the latency, for example, from Little's law, same amount of parallels, I might get twice the throughput. Let's say for sake of this argument, you've already minimized latency as much as you can. So now you're coming down to what can you do? Well, banking is the trick, right? So with banking, we're going to make the memory seem like it's still one memory, but it's higher bandwidth. And internally, we're going to have multiple memories, right? So instead of having one big memory, which maybe doesn't have enough ports, we can have that look like one big memory, but internally it's perhaps two memory banks. Each bank provides a port. And so the result, we can provide twice the request than what we could as one monolithic memory. So in other words, what we're doing is we're not decreasing latency. Latency is the same, but we're increasing parallelism. And by Little's law, increasing parallelism, same latency means increasing throughput, right? This is the kind of thing that, of course, can be parameterized very nicely in Chisel and can be really helpful, right? Okay, so let's say we're bringing these across banks. How do we do this? Well, there's two ways to do it. Number one, you can just say, okay, for memory and providing, each bank handles, one nth of that data. Sure. And so as long as, you have logic in there to figure out how to get the request to the right bank and the request for data is uniform across all the addresses, that way you're not overloading any one of those banks, that works out pretty well. Sometimes you may have a situation where you want to have really high read access and maybe the access patterns are non-uniform, in which case you want to make sure that no bank is overwhelmed. You actually have all banks hold the same data, in which case you're replicating, right? So the replication increases the cost in terms of number of memories you have. However, because of the throughput you're getting, perhaps it's worthwhile, right? All banks have the same data. This works great if you want to get lots of read access, but if you want to do lots of writes at the same time, it's not going to help you, but it's a start. Here's what you can do under the hood. Well, you can figure out, are these banks going to have their own independently exposed ports? By extended ports, I mean exposed to the outside world, or are they going to appear to be a single shared port that internally is routed to the right port. So in that prior slide, these memories had that ports externally exposed. Instead, maybe if the requests are take a lot longer time relative to the transfer, you can have just a single port and internally kind of fans out, right? And of course, what about very big memories? Sometimes you're forced to use multiple memories just because you need the capacity, right? So it's not because you want performance or latency, it's because of the capacity to have all these banks. And even still, a lot of these banking insights still apply. And there are some scenarios where you actually end up in a situation where, in order to get the capacity target, you actually have surplus bandwidth, right? You wish you could actually spend less on bandwidth, but you kind of are forced to get there. Um, if you look inside of a DRAM chip, you'll find that uh, the DRAM architects kind of had to play this game a lot. In order to provide the capacity, they've made certain trade-offs, and they've tried their best to not waste bandwidth internally. But if you have a DRAM chip that has gigabytes of data on it, and you're accessing 64 bytes, i.e. 512 bits at a time, most of that chip is not doing anything, right? And so how do you make that work out is an interesting architectural challenge. Cool. Yes. I should say, instead of accessing, you forget it's transfer latency. Yeah. Yeah. Basically, the situation is, if some of the shared versus replicated ports or independent ports, right? If, it takes, let's say, 1 nanosecond to transfer a request and 100 seconds to get the data, then sure, having one port for both banks makes sense. But if it's 1 second to transfer and 1 second to request, then they're going to bump into each other, right? So it's kind of that's what that comment is. So yeah, so you can this is either access or transfer, whatever you want to call it. Cool, good questions. Okay, what else can we do to make memory work better? Smoothing out demand. This is actually I pitch it here in terms of memory bandwidth. This is a universal problem in engineering. And for example, even here in our own campus, if you've ever run into traffic, you've observed this, right? In the real world, we often have very bursty demand, such as everybody driving right after class, right before class, right? Uh, you go in one of these roads on campus at 3 a.m., there's not a car in sight, right? And so, like, you've experienced that. You experienced both waiting forever in this line of traffic, thinking, man, I wish there was more roads here. But also, if you were here at other times, you see this road is not going to see a car for 4 hours, right? And so, um, there's that burstiness to the traffic, right? The traffic is non-uniform over time when it arrives. And so, as a result, you kind of get caught in a situation where if you want to handle these peak demand situations, you got to build a much bigger system, right? More roads, more lanes, or in a case of memory, more memory bandwidth, right? However, if you have a really bursty traffic, there's sometimes you're not using it, right? This is wasted. It's all this cost you're not using. If you build 4 lanes in the middle of campus and it's going to be quiet in the middle of the night, is that worth it, right? So this gap between the peak versus the average is what is commonly a really engineering challenge, right? Because if you build less than the average demand, okay, at that point you're just in trouble, right? Because under no amount of time you're going to get yourself safe. But if you have a capacity that's greater than the average, but bursty traffic, that means that sometimes you're going to see long queues, but other times you're going to be empty, right? So they're going to drain. For example, if you travel and you fly, look at TSA, right? They're constantly putting staff on and off shifts to like try to balance the staffing at the security checkpoints in order to make sure that matches what's needed. And someone is always aligned. Turns out it's always aligned. That means you're not wasting their time, but it means you're wasting your time. Um, so, how do you get the gap between peak versus average to be reduced? Smooth the traffic, right? If you have bursty traffic, try to do whatever you can and make it like it's smooth. In which case, you pay for this. In which case, it's much cheaper, right? But in some scenarios we've all dealt with, right? There's a gap. We can't smooth out the gap, and they pay for peak, and it's a lot, right? So what can we do to smooth out traffic? Well, in a controlled world of architecture, we can do two things. We can pipeline and double buffer. You're going to see both of those in the next few slides. Um, so one idea, what we call overlapping communication and computation, right? Or you can think of it almost like pipelining in a way. In other words, uh, if I have some system where I need to both perform computations and then communicate, I move data for next computation. If I do only with activities at a time, some part system is going to be idle, right? So ideally, what I would do is I would overlap the communication with the computation, at which point there's less idleness, right? So of course you can see on this diagram here, you're going to have to spend less time there. That's great. Now, what are the caveats, right? In order to pull this off, that be communicating one thing and computing on another thing, you need two things at least, right? So there's some amount of parallelism here kind of needs to be required, right? And so usually you have that parallelism and you can pull this off, right? So you can kind of communicate and compute at the same time. Does anybody know the maximum speed up possible from this optimization? Just think like a limit wise. Could I get 10x this way? I see a no. Okay, why couldn't I get 10x this way? Yes, the two's the right answer. Yes, exactly right. So 2x is the limit. And that's the best case, right? You might only get 1.2x, right? But basically, so what's the reason why 2x is the limit? Let's say your computation is 90% of the time, communication is 10% of the time. Okay, if you overlap that 10% is communication with computation, great. You save 10%. You still have 9% of the workload there. So the extreme case is you have 50% computation, 50% communication. You overlap those two perfectly, 2x, that's the limit. So it's still worth doing, but it's 2x rather than a huge thing. Um, cool. What else can you do? So one way to implement what we're just talking about is something called double buffering, right? So let's say you want to overlap communication and computation, but we talked about before, right? Maybe you have a port limit in memory or something. So what can you do? Well, you can actually have two memories. This is like banking, and or it's even could be buffers that your software inside of your memory, and you write to one and you work in the other one, right? So in other words, you see in phase one, computing's on memory one, communications on memory two. In phase two, compute's on memory two, and communications on memory one, right? So basically, you just have two copies, and that way you kind of can work on one and copy the other. This is extremely commonly done, right? This is pioneered decades ago for things like monitor, where you have the buffering for your display, where you have one display that's actually being rendered to the monitor, and that's another buffer is being written to for next frame, right? Cool. So when it comes time to actually essentially memories in your architectural design, what can you do? Optional memories, like I said, you're going to really plan those out, right? It's not something kind of change late. You're going to know from your early modeling as well as you start building it what your cost targets are, your performance targets, etc. There's so many pins involved. It involves so much in packaging, entire system design that it is hard to change those things late. So you're going to know if using HBM, it's a very different experience using HBM than it is using, let's say, LPDDR or DDR, right? That's a huge change to the rest of the system. For onto memories, you have some choices, right? I'm using registers, I'm using SRAMs. You'd love to use SRAM when you can because it's denser, i.e., cheaper. You get more bits per square millimeter. Like I said, you get these usually from it's a component you gotta get tracked down. So hopefully you get them from the foundry. Uh, Previously, you had to get something called a memory compiler where it had to, you tell what parameters it wanted and you would make a memory for you. Perhaps doing some of the banking internally for you automatically. In some ways, if you have a memory compiler as like an OG hardware generator. Um, and either way, there's some real physical constraints here, right? How you tweak these parameters, find the right ones to match, both find a combination of things that are already available, what matches your design, maybe to make your design contort to match them, etc. Um, on FPGA, you actually have a whole bunch of choices, right? So depending on your vendor, um, you have registers, sure, great. Sometimes you get something called LUT RAM. You can turn those logic elements into RAMs. You can have BRAM, you have URAM, all sorts of types of memories. If you're a veteran FPGA developer, you might be used to instantiating these manually in Verilog. And if that's something you really want to do in Chisel, you can. You can, put those instantiation codes inside what's called a Verilog black box, and it looks like Chisel from the outside, but of course inside you have that Verilog is exactly what you want to instantiate the thing directly. That works. In the Agile philosophy discourse, I really encourage people to avoid doing that, right? Try to have your code written in a way where the tools will correctly infer the need to use these memories. The reason why it's better is it often is not only more portable, it's also going to be better performance, right? So sometimes you have a design that has a lot of demand for capacity. You hope the FPGA uses VRAMs, right? That way it gets a lot more capacity available. But at some point, maybe it's going to run out of VRAMs, or at some point, the VRAMs that are available are so far away from the rest of your design, you actually wish you would do part of that not on VRAM, but actually using registers or LUTRAM to be closer and keep it more dense. If you tell the tools, hey, you must use VRAM, that's the optimization parameter you're taking away from the tools. So actually, you'd rather have the opportunity. And so, yeah, if you write your Verilog in the right way, at least the Xilinx tools are pretty good. Herdal tools are not bad at it, and inferring when you can use these memories. And so sometimes you get a little nudge, but usually they're pretty good. And so try to write your code in a way that it infers the need for these memories rather than instantiating them directly. And then in terms of what does Chisel provide? Uh, Chisel describes behavior at tail level, right? Okay, this is a memory which is read in zero cycles, i.e. a mem. This is a memory which is read in one cycle, a sync read mem, right? And so you also set latencies in various amounts. That's sufficient for, like I said, registers, VRAM, URAM, etc. If you want to use a specific vendor SRAM, you have a few choices, right? You can go ahead and stitching together post Verilog generation, or you can make a black box to wrap it. Chisel was to specify read and write ports. I believe that was lecture 6. We talked about that, etc. Questions? Cool. So today, so it was kind of this leap into this new shift for talking about physical design optimization of this course, much more high level. And memory optimization, like I said before, uh, designing hardware takes a lot of effort. You only want to know when you're optimizing that you need to optimize and where is this place to be most productive, right? And so understand where you are. This agile process of getting the tools working early, closing the loop early, seeing your costs early, helps you kind of identify where to spend the most time and effort. And I've talked a lot about architecture in the second half of this lecture, talking about Little's law to kind of understand about how to reason between latency, throughput, and parallelism. And we talked about memory, which is the first thing you should optimize. So architecturally, get your memory figured out. What technologies you're using where, how can you reduce those costs. That's going to be a way bigger cost reduction than anything else we're talking about. And so then assuming you get memory figured out and your memory optimized, then that's going to be next lecture's optimizations. Cool. Any other questions? Okay, thanks, folks.